Right, so this is now the opposite. So this was the first video where we're, instead of previous things, the motors, the loudspeakers, it was using current, using magnetism to create things that are going to move. This is the opposite. It's still using magnetism, but it's moving things to create current. And that's the generator effect. Again, very specific terminology that I've gone through the exam papers to find. So when a conductor moves relative to a magnetic field or a magnetic field changes, a potential difference is induced across the ends of that conductor. Your conductor could just be a wire, or it could be a bar, whatever. Now, if the conductor is part of a complete circuit, then a current is going to be induced. Now, this is a bit tricky, but when you then have a current induced in a wire, there's also going to be a magnetic field around that wire. And as it happens, what happens is that magnetic field around the wire opposes the change to cause it. So if it's like heading towards a north pole, it's going to create a north pole itself to try and repel it back out of the way. That's a very tricky thing for GCSE physics. Even at A-level physics, it's called Lenz's law. It's very tricky. But if you just try and remember that this induced current generates a magnetic field that opposes the change that cause it. So here's an example of it. So I've got a little magnetic thing here with a magnetic field going from north to south. And if I move this wire up and down, perpendicular to the field is going to be best. If I move it up and down, I'm going to notice my ammeter fluctuating as I've generated a current. Because what I've done is I've induced a potential difference. So these electrons here get kind of like jostled around by the magnetic field. These not so much, as a potential difference induced, and then that will induce a current in this complete circuit. But like I say, as I'm doing that, then all of a sudden I also get a magnetic field created around this wire, and that's the thing that opposes its motion, so it makes it quite hard to do that actually. Now, the size of the induced current and the induced PD depends on the magnetic field strength. Stronger magnetic field, a greater induced current and induced potential difference. The length of the wire in the field, so quite often what we do is we coil it around to get a lot of the wire in the field. The angle, it's best when it's perpendicular, so when the field lines are perpendicular to the wire, that's when it's the strongest or the largest current potential difference is induced, and the faster you go. It's all about cutting through these field lines. The more you cut, the better. Now the direction of it, well, the direction is not necessarily something we're going to have to calculate, but I can tell you that if you reverse the magnetic field, you reverse the direction, or if you move it down when you're moving it up, you also reverse the direction of the current created. So kind of moving it up and down like that would create an alternating current, because the current would go one way, then the other way, then the other way. Does that make sense? Okay, so next on to how we can use this to generate electricity.